Hello and welcome back to our continuing series of lectures on our NPTEL course on advanced plasticity of solid continua. So we have been discussing about the thermoviscoplasticity for some time, and now that we have already seen in the last lecture a rationale for the rate functional to be the right objective for minimization to get your solution, we must do it in a way consistent with the way that we should be able to implement it within a finite element method and hence in a computer, right, to get actually the solution numerically. This is exactly what we try to do now. We do a time discretization of the entire, because plasticity is a time dependent process. So we do a time discretization, and over the two consecutive time instance, let us say Tn to Tn plus 1 over the time step, we find the incremental potential, okay, and minimize it. So this is the idea now, as we have been actually been doing for some time also for other problems like the viscoplasticity problem without the thermal effects, okay. So we will do the similar thing here. Alright, so let us actually start with the time discretization. Now before that, remember that basically what we are minimizing now is integral 0 to t L dt, right. So over instead of doing it over the entire time, this is actually an integration of 0 to t1 L dt, right, plus integral t1 to t2 L dt and so on, right, it goes on. So basically what we are doing, we are actually doing a time discretization starting from t0, then t1, then t2, like that, okay, and then consider a typical such time step from Tn to Tn plus 1, okay, right. So I mean, assume that the time step size is basically delta t, Tn plus delta t is Tn plus 1, okay, and define the corresponding increments, okay. So basically delta epsilon, the increment in strain, is epsilon n plus 1 minus epsilon n. Similarly you do define the increment of the plastic strain, okay, like this, and also define the increment in the other internal variables, delta alpha equals alpha n plus 1 minus alpha n. So it is obvious that epsilon approximate the rates, okay, we have to approximate the rates over the time interval delta t as delta epsilon p by delta t equals approximately epsilon p dot, and similarly for alpha dot, okay. So this is the approximations that you have to do within a time recursive algorithm for implementation within a computer, okay. Now let us come to the minimization problem, okay. So we are essentially minimizing the integral of L over the entire body, let us say, right. So basically the incremental, so integrate that, so call it pi, right. So L is the rate functional, its integral over the body, right. So essentially what we are doing here, yeah, okay, so what we are doing here is integrate this over Tn to Tn plus 1 and call it psi n plus 1 minus psi n, because this is the increment, and the delta t factor multiplies this phi, which is the rate, the dissipation functional, and the dissipation functional is a function of z dot, right, all these rate variables. In this particular case it is a function of the epsilon p dot and alpha dot, all right. It is also a function of q, and it also depends on theta, all right, all at n plus 1, okay. So now the incremental potential, therefore, if we call it by script or calligraphic j n plus 1, right, that is equal to this sigma psi evaluated at n plus 1 functions of epsilon n plus 1, theta n plus 1, alpha n plus 1, all that, minus psi evaluated at Tn plus delta t times phi, which is considered as a function of these approximate rates now, okay, delta epsilon p by delta t and so on. So, recall that we are actually solving for the plastic solution at Tn plus 1. So, that essentially means that we already know the solution at Tn. So, therefore, all the this quantity is known to us, right. So, when we take the variation, when you do this stationarity, this quantity is of no use, it is out, because we are not taking variation with respect to things which are known, right. So, therefore, the only quantities that actually come into play which occur in the variation in the minimization problem is basically this, right, only psi evaluated at Tn plus 1 and of course delta t times phi written as a function of approximate rates, okay. So, this is what we do now. Now we have to recall a few things. We are considering a specific form of the dissipation potential, right. For the Perzina model that we have been considering for the thermoviscoplasticity problem, the dissipation potential has 3 parts, okay. One is corresponding to the rate independent part, okay, which is basically, you know, I will come to the details of this lambda. This is the rate independent part. The other part corresponds to, you know, the rate dependent part, rate dependent viscoplastic part for phi. C theta is you know, it contains the viscosity. That means if the viscosity parameter is 0, then C theta will also be 0, okay. So, and then, you know, you have this lambda coming in here too in the Perzina model, right. The rate independent, some aspects of that rate independent part will be coming here too, okay, if you recall the structure of that Perzina model, and there will be a thermal part of phi which is given here, okay, which is quadratic in the heat flux Q. Now, let us come to the details of how to find this define this lambda. This is the phi rate independent part of phi, right. So, this lambda that we have is basically the, you recall that basically, you know, in the context of standard plasticity, lambda is related to epsilon p dots norm, right. So, similarly here the only difference is that we really cannot take only epsilon p dots norm, we have to take alpha dots norm also. So, this is the joint stuff, right. So, both related to the rate of epsilon p approximately done through this finite difference and rate of alpha, okay. So, therefore, we can actually, because there is a delta t factor multiplying phi in the rate functional, so therefore, the whole thing has to be multiplied by delta t, right. So, delta t comes in everywhere in all the terms. So, if you multiply this by delta t, right, given the degree 1 homogeneous, you know, structure of lambda, if you recall that when we discuss rate independent plasticity, this you know, the phi had a degree 1 homogeneous structure, right. You know, so for a degree 1 homogeneous structure, this delta t as a factor will come out simply of this, and you can just write it as, so since this factor comes out as 1 by delta t, you can multiply lambda by delta t and write this as just the norm of increment of epsilon p and increment of alpha. Now, you see these dots are no more there, okay. We have actually replaced it by just increments of the variables which are internal variables, all right. So, this is the situation. Now, the final incremental potential therefore with all this discussion can be written in this manner, okay. So, psi evaluated at n plus 1, that is the first term, and psi is a function only of the elastic part. So basically that is the total strain minus the plastic part minus the thermal part, all evaluated at time Tn plus 1, the temperature at n plus 1 and alpha, the internal variables other than epsilon p at n plus 1. Okay, and this is the start of these 3 components of phi. So this is the rate independent component of phi, appropriately modified as in the last slide. Okay, this is the viscoplastic component of phi, okay, multiplied by delta T as in the last slide, and this is the thermal component of phi. All right, so this is the functional, the incremental rate functional, incremental potential to be minimized for at each integration. So if you are not using, if you recall that we actually do it in 2 steps. One is in which we do the integration over the entire body, that is called the structural update. But before that, that is the next step. Before that we do the local update, in which we do not do the integration over the entire body of the rate functional, but consider the rate functional only at material points, typically the Gauss points of integration in your finite element framework, right. So that is what we are doing. So basically this is the rate functional in the incremental form written at a specific material point, all right. Now so this has to be minimized at each integration point, right. And then if I have this at each integration point, integrating is no problem. You just multiply this by the appropriate weight, the integration weight, Gauss weights, Gauss quadrature weights, and then you get the integral. Okay, so at each Gauss point, what are we trying to find? Our objective is to find out epsilon n plus 1 p, alpha n plus 1. These are the internal variables to be found given your total strain epsilon n plus 1, the temperature at n plus 1, it should be known, and the last available value, that is at Tn, the available values of these internal variables, right, at the last instant, available instant. Okay, so we do so therefore by minimizing this j n plus 1. Towards this there is a similarity that is going on everywhere. Okay, so as before, if you recall that we have been defining a trial stress first, assuming that everything is elastic, there is no plastic flow at all. So that actually you assume, so that is purely based on an elastic analysis. So that sigma trial is the elastic stress given by the derivative of the elastic part of psi with respect to the elastic part of the strain, right. Now the variation of the energy, that is the free energy, if you take the variation of the free energy, that will give you, because you have to hold these thermodynamic force like objects like sigma here fixed, that we have been discussing for some time, only the rate like variables will have to be modified, virtually varied. Okay. So this becomes this, so minus sigma n plus 1 in a product with variation of epsilon n plus 1 p. So the variation of the dissipation, okay, so the variation of the dissipation, this delta, this is basically the rate independent part of the dissipation potential. So if you take the variation of that, that is nothing but the partial derivative of lambda, subdifferential of lambda with respect to these 2 quantities, that is delta epsilon p and delta alpha. Okay. And you have also to take the variation of the viscoplastic part. Okay. That viscoplastic part, if you take the variation, then you get again you can write it in terms of the variation of lambda and this factor. Okay. So you understand. So in both the cases the variation of lambda comes into play. So this is the rate independent part, this is the rate dependent part, the variation of the 2. Okay. Now the stationarity condition in our language as before will be in the written in this manner. Essentially, you are more familiar with 0 equal to this, but you can understand it that way. Okay, so 0 equals this, right? So you see that because the variation, if you take this comes out as a factor, right? Similarly, you can just take out the appropriate factors out, so that the coefficient of that factor is just this. Okay, so this tells you that basically, so this is one of the equations for which we are taking the variation with respect to delta epsilon p, all right, and you have also to take the variation with respect to delta alpha. So we have written it in 2 equations instead of writing in one. We have written it in 2 equations. First take the variation with respect to delta epsilon p, then take the variation with respect to delta alpha, and you get these 2 equations. Okay, right? You see this factor is common, this factor which multiplies here delta, the subdifferential of lambda with respect to delta epsilon p, and here it multiplies subdifferential of lambda with respect to delta alpha, but both of them are the same. I mean, the factors of both of them are the same, that is 1 plus c times delta t times lambda to the power 1 by m. Recall that m is the rate sensitivity exponent, right? So now let us call this by gamma. Okay, this quantity you can call by gamma, right? Therefore, what do we have? That you take sigma n plus 1 this side, x n plus 1 this side. We basically have that sigma, the sigma n plus 1 and x n plus 1 must belong to or equal to, if everything is smooth, gamma times the subdifferential of lambda. That is now with respect to combined delta epsilon p and delta alpha, combined incremental internal variables. Okay. Now recall our discussion about 2 lectures ago. We discussed that gamma here has the same structure. This gamma here we have been discussing about this Minkowski functional or gauge, right, as a certain, if you take this all the forces, thermodynamic forces, and take the norm, right, properly, you get a Minkowski type functional gauge over the set C, script C, of all generalized stresses, right. So gamma is such a Minkowski functional over the set C. Now if you take gamma, right, gamma is basically a norm of the generalized stresses, right. What are the generalized stresses here? Sigma and x. Okay. If you take this norm over the set C of that set script C consists of all sigma x such that the f, the yield function there, is less than equal to 0. That is corresponding to rate independent case, right, and that is rate dependence has not yet occurred. Then that is one way of looking at lambda, right. But in rate dependent problem that we are discussing now, there is no guarantee that sigma and x together will be in the set C, script C, right, because it can cross there. We call that as overstress, you recall that, right. So therefore this gamma is exactly that. It is basically the amount by which you have to expand, that amount is tau, that amount by which you have to expand. Let us say script C is a spherical set, like in von Mises theory, okay, of rate independent plasticity. The original yield set is spherical. The factor by which you have to multiply that sphere is basically the overstress, right. That is the overstress that is beyond f equal to 0, right, and the so your gamma is basically that particular overstress that corresponds to the current stress levels. You understand? So what I mean is that this is my, let us say, script C, okay. This is my script C. It is very difficult to write script C that way, okay. So this is my script C, and my actual stresses may have gone here. This is sigma x, okay, it is here. From here it has gone this much. According to the normality rule, it must have gone this way, okay, normal to the so called yield surface. Now, if you take a new set of admissible stresses much bigger, then sigma x belongs to this bigger set, but we are looking for that particular set through which such that the boundary of that will pass through sigma x, right, and this is exactly that tau, that factor by which you have to increase this script c to get that particular value for sigma and x, okay. So that is nothing but the overstress. So gamma is therefore something like the overstress, and it is nothing but f itself, you understand, because this is the value by which f has exceeded 0, f the yield function has exceeded 0, correct. So this is an important insight here. So basically we assume f to be degree 1 homogeneous. So basically we have already seen that gamma is basically equal to f, the overstress. Now we can actually, so there is no guarantee how much the value that tau will be, but for ease of implementation we can always normalize things in such a way that tau will always be equal to 1. You understand, in that case f will be always equal to 1. Whenever f exceeds 0, I can normalize that value appropriately by dividing by that value itself, so that f is always 1. That normalization is helpful because you do not have to actually do with a variable value of f, right. So this is called the unit level set, the unit ball of the gauge, okay. So call it by script C1. This consists of all sigma and x, the generalized stresses, such that gamma, that is the overstress, is less than equal to 1, right, and hence it is the set of all sigma and x, because gamma is equal to f is less than equal to 1, okay. This is just the rescaled version of the yield surface, nothing more, okay. So f less than equal to 0 is the elastic range. So for any s greater than 0, sigma x must belong to s times the set C, which implies and is implied by the fact that f is less than equal to s, and use the duality now, okay. Now if you have understood this part, then what it actually we get by taking the differential of lambda with respect to the rate quantities is just those stresses, right. That is basically the flow rule corresponding to f equal to 1 after rescaling. You see, that is my lambda, the del lambda, okay. So that I hope you have followed this, okay. If you have not, then go through what actually my arguments once more, okay. So maybe repeated exposure will help you understand better. Now let us go through the steps that we have to follow, okay. So the first step is the elastic predictor. So this is sigma trial, standard, okay. Corresponding to this sigma trial, purely an elastic prediction, you find the corresponding f trial, okay, because you know your sigma trial, you know your last value of xn, because you have not yet updated your xn, okay, theta n plus 1, last value of xn means at the last time instant Tn, okay. There you have already updated it, it is assumed in a recursive framework, okay. So f trial you have found. Now check the admissibility. If f trial is less than equal to 0, then of course we have not yet gone past the yielding. This is a viscoplasticity model of the Perzina type, so there is yielding. So in that case the response is purely elastic. That means that epsilon p at n plus 1 is the same as epsilon p at n, and alpha n plus 1 equal to alpha n, that is the plastic flow has not happened, right. So this is simple, but the more important thing is step 3, which is the plastic correction, okay. If f trial turns out to be greater than equal to 0, that is the last condition is not satisfied, then we have to solve for the plastic multiplier, the increment of lambda, which contains the increment of both epsilon p and alpha. Okay. So, because the normality rule is typically valid everywhere, right. So, basically what actually we are saying is that the flow direction corresponding to sigma, because f is now a function of both sigma and x. These are my forces, not only sigma, x is also an extra force. So, corresponding to sigma we have epsilon p which produces power, epsilon p dot. Corresponding to x we have alpha dot, right. So, the flow direction corresponding to sigma is del f by del sigma, right. So, we have the following updates. Similarly, the flow direction corresponding to x will be del f by del x, you understand. So, NP is one flow direction corresponding to sigma, one of the generalized forces. The other generalized force x has another flow direction h. H and NP need not be the same because H corresponds to hardening, right. So, they are different phenomena altogether. Now, okay, so you can actually do these updates provided you find some appropriate governing algebraic equation to find delta lambda. You can, we have not yet said how to find delta lambda, but if you know delta lambda, then epsilon n p plus 1 can be found simply by adding to epsilon n p delta lambda times n p. Similarly, alpha n plus 1, but here it is delta lambda times h. Okay. So, these are trivial. What actually is important here, what is the equation for delta lambda? So, this is the consistency equation from the Perzina structure. So, delta lambda, if you recall, is basically delta t times the Macaulay bracket of f, that is the overstress, right, divided by the viscosity to the power this exponent m, right, for the Perzina model, right. So, this is essentially an implicit nonlinear scalar equation for delta lambda, because sigma n plus 1, x n plus 1, these are all functions of delta lambda, okay, because of this following thing. Sigma n plus 1 is sigma trial minus the elasticity tensor times delta lambda n p, correct. Similarly, x n plus 1 is x n plus delta lambda h n plus 1, okay, where h is del f by del x, n p is del f by del sigma, correct. So, you see that if you put this back here, all this back here, then you see that these are functions of delta lambda. So, delta lambda is on the left hand side, on the right hand side both. So, this is basically implicitly defined nonlinear equation for delta lambda, right. So, if you solve for delta lambda, then you get your final solution for everything. Now, let us take a very special case, von Mises isotropic hardening, right. Let us take this Q to be the effective stress, okay, so and sigma y alpha, a alpha dependent, internal variable dependent, yield stress, right. So, let us take x equal to 0, that is there is no back stress, simple thing, right. So, no x. So, there is only one flow direction here basically, no, the NP is basically here is del f by del sigma, which is basically given by 3 by 2 S by Q. S is the overstress, and this stress correction is essentially radial, okay, because del f by del sigma is the radial direction, right, for the corresponding f, that is the yield function. So, the hardening depends on alpha, this alpha here, okay. So, f n plus 1 is equal to q times sigma trial minus the plastic correction delta lambda c n p minus sigma y as a function of alpha n plus delta lambda, okay, updated alpha n. So, explicitly if you want to write, you see that lambda, delta lambda is such a nonlinear function depending on q and sigma y, the form of q and sigma y. This is the nonlinear equation you have to solve for this particular case of von Mises viscoplasticity with isotropic hardening, right. This is the nonlinear, you can solve it by, let us say, the Newton-Raphson method, or by Newton-Raphson is the typical thing, right. So, that is what basically finite element uses. So, it is in this context, if we want to solve the whole thing now by a Newton-Raphson method, you know. So, we need to actually develop a tool for that. You know what the tool is. It is basically the consistent material tangent and consistent tangent stiffness that we have already done for viscoplasticity and other problems, for rate independent case also, but for this thermoviscoplasticity we have not derived that you know, material consistent tangent as, and from there the tangent stiffness. So, that is what we will be doing in the next lecture first. Okay. How to do the material tangent stiffness, so that instead of solving these equations by any other means, we can actually do it in the same way that we use elasticity, nonlinear, we solve nonlinear elasticity. Okay. So, after this is done, we will start with our discussion on strain gradient plasticity. So, strain gradient plasticity is a very special form of plasticity, wherein you have in the free energy not just the plastic strain which has to be deducted from the original strain, overall strain, to find the free energy, but also the gradient, the derivative with respect to the spatial coordinates, the gradient of the plastic strain, defining additional energetics associated with the free energy. Okay. These things happen when you have typical band formation in during plastic flow. Okay. So, we will be discussing this in the in one of the lectures to follow. Okay. So, with this we will be concluding this talk, this particular lecture, and I will meet you again soon in another. Thank you so much for your attention.